If you want to observe the morphology of peripheral blood under the optical microscope, you mostly need to prepare a blood smear. So this is a simplified explanation how to do that. You will need 2 histological slides for that. That should be clean. You will apply 1 droplet of blood on the edge. You will touch it with a 2nd histological slide. So due to the capillarity, there will be a meniscus here, and by simply sliding the slide forward, approximately under this angle, you will produce preferably single layer of 4 blood elements. And that need to be fixed and stained. The most classical method is a combination of 2 methods called May-Greenwald and Gimsa-Romanovsky. I'm mentioning these 2 methods because from these we got the terminology of the peripheral blood elements like neutrophilic, basophilic, eosinophilic, etc. Then find a systematic way how to observe the slide. So you will start in some region. Here is usually thicker, and there is a thinner layer. And you will find your starting position, move to the edge, then move 1 width of your field of view and go back and simply systematically meander your slide to be sure you will never come to the same position twice. And you will need oil immersion objectives for that purpose. So that means if you have the slide, you will apply a special objective called oil immersion objective. This objective uses the benefit of applying a droplet of oil between the slide and the front lens of the objective. So you will apply 1 droplet of immersion oil. That has a refraction index like 1.33, thus permitting more light rays to enter the front lens of the objective. This can be measured by the half aperture angle called alpha, and this will increase the amount of rays carrying the information about the structure of the slide and participating on the formation of the image due to the refraction theory. This will increase the resolution of your observation. And due to this famous equation used by Ernst Abbe, a famous microscopist, the optical resolution equals the wavelength of the light you are using for observation divided by 2 times numerical aperture. Now, numerical aperture is the property of your objective. Let us take example of numerical aperture. For example, 1.25. It's n, which is the refraction index here, times sinus alpha, which was the half entrance angle. And if you try to calculate the resolution, how it's improved by using this immersion oil technique, let us say the wavelength would be 550 nanometers, which is approximately the wavelength of the green or green-yellow light to which the human eye is most sensitive, and it's like in the middle of the range of wavelengths of observable light, divided by 2 times 1.55, which is the numerical aperture of the objective. You got approximately 220 nanometers. Nanometers, which is 0.22 micrometers, and there's a theoretical best resolution limit of your observation. Of course, the real resolution limit would be worse, and the resolution is defined as the distance between 2 objects that could be discriminated as separate objects, not merging into a single one. So this is to explain why are we using this technique, why do we need that, because for good observation we need lots of details that could not be increased only by magnification of that objective, but what we really need to improve is the resolution. That's why we use the all immersion objective observation technique.